YouTube. Okay. We are going live. We are live now.
Hello.
Yeah.
Now.
Yeah, hi, hello. By the Academy of Space Renaissance International, and my name is Sabine Heinz. I'm the person responsible for our webinar series. And on this 8th of May, 2023, I'm really delighted that you have to come to join us. Today is also the day of the liberation from the Hitler fascism. So we should remind always to this, and above all, that we see now that we have war again in Europe, and yeah, I hope this war will end soon, and that we will create a peaceful world. Our today's special guest is Ulrich Köhler, Dr. Ulrich Köhler from the German Aerospace Center, DLR, from the Institute of Planetary Research. And I'm really, really happy that he is again our speaker, because I love his lectures. Hello, Uli.
Sabine, welcome.
Yeah. And Uli will talk about JUICE, the journey to Jupiter, very actual topic. And I also would like to welcome Professor Bernard Voing, our president. Hello, Bernard.
Hello, do you hear me? So yes, best welcome to my very long-term colleague and friend, Uli. We have been working together on Mars Express, stereo camera, and also we have had a number of events together with DLR. So yes, we are very pleased. I'm now on currently in France after a series of trips where we have been to the Ibiza Eurospace Hub Forum. We have been also at the European Geoscience Union, where we have seen also some long-term colleagues. And also, of course, we have this memorable launch of JUICE. Actually, I was attending it from ESTEC at the European Space Agency. And now we are going to hear about, yes, why we do JUICE and how fascinating is this world, the Jupiter stellar Jupiter planetary system, together with this very interesting icy moons. So yes, very much looking forward, Uli. And also we have seen Uli at previous events at the Space Renaissance Berlin Festival, where also he has shown our activities in just making interesting the exploration of space and of the solar system. All the best.
Oh, thank you for those nice words, Bernard. And also I would like to welcome Adriano Ottino, our former president and one of the founders of SRI, and now vice president of SRI. Hello, Adriano.
Hi, thank you very much, Sabine, and yeah, very welcome to everybody to listen to this quite interesting lecture by Ulrich, and I take this opportunity to remember that we are collecting signatures on our proposal for an 18th SDG, Sustainable Development Goal, to be added to the 2030 UN agenda. I will post the link in the chat so everybody can put their signature on the pledge. Very important, we have to collect thousands of signatures. So,
yes,
okay.
This is true. Thank you, Adriano, and for this important advice. And before I give you the floor, Uli, I would like to introduce you to our audience. Ulrich Köhler is a planetary geologist at DLR Institute of Planetary Research in Berlin. He studied geology in Munich and spent a year for his diploma thesis at Universidade Estadual Paulista in Rio Claro. I guess you speak Portuguese. At DLR, he started 1991 with the analysis of multispectral imaging data from NASA's Galileo probe, passing the moon twice and arriving 1995 at the Jovian system, transmitting image data from the Galilean satellites. From 1999 to 2000, he was at Brown University on a NASA grant, And returning to DLR, besides the moon, his focus then was Mars, where DLR has the famous high-resolution stereo camera in orbit on ESA's Mars Express orbiter. And Ulrich is the coordinator of the Institute's education and public outreach research activities. Ulrich, Uli, the stage is yours.
Okay, then I try to get my pictures on the screen. Yeah. Okay, can you see something?
Yes,
Yes.
we have a full screen.
Yes. And I want to ask Bernard whether he can remember when Mars Express was launched. We were both much younger.
Oh yeah, we all.
20 years ago.
Yes.
On June 2nd, 2003, we sent the first European planetary mission to another planet that was Mars, and Mars Express was the name of the mission, and it's still running. It's really a wonder and a wonderful mission. And now ESA is going to a bigger target, namely to Jupiter with a JUICE mission, the Jupiter Icy Moons Explorer mission. And what you see on the screen is a rare constellation of Venus, which is the brightest spot. And between the red lines, there's Jupiter and there's Mercury too visible, which is really seldom the case that you can see Mercury. And I want to tell you a little bit about the target, about the mission objectives, about the mission itself, and about some of the experiments. I hope that I can really make it until we finish this hour at 10 o'clock Central European summertime. But, you know, I'm a famed and infamous talker for too long presentations. So
You can talk as long as you want to.
And we all know it's Jupiter is a little bit further out than Mars, so and it reminded me to the song from the Dire Straits, so far away from me. But thanks to the developments in spacecraft and in carriers and all these things, we can really reach all these targets now. Not easily. It's still really challenging thing to get a space probe all the way to Jupiter or to Saturn or even to Pluto. We all have experienced this, but they can do it. The rocket scientists, they can do it. And that's really a nice thing. So I never expected when I came to DLR 32 years ago that I would experience more missions than the Galileo mission, which, by the way, was not an ESA mission. It was a NASA mission. After Galileo, there was Cassini to Saturn. After Cassini, there was Mars Express. There was Venus Express. There was the Smart 1 mission to the moon, which is still my favorite target. The closest target is the least observed. That's a pity, but this changes in this decade, luckily. And so we're going now to Jupiter with that spacecraft here, which is called JUICE. And it has to do with the search for life, because that's the bottom line of all these missions, or of many missions these days, that we want to find out in this century. I say it in a bigger scale, in a bigger time frame. We want to find out in this century whether life in this solar system, at least, was only possible on Earth, or whether we have other worlds like Mars, of course, which is the prime target for searching for life, but also icy moons of the big planets in the outer solar system, like Jupiter's moons Europa, Ganymede, and Callisto. And so it took a long time to get this mission to launch. And on April 14th, it was finally the case, or 13th, it was finally the case. 14th, it was the case that we launched successfully with one of the last Ariane 5 rockets, and everything went smooth and perfect, and the spacecraft is on its way. There are 11 experiments on board. I will touch this, of course, and as DLR, we are proud that we have one PI experiment. This is Gala. So from Gala, we have the principal investigator for this experiment, and we contributed significantly to Janus, the prime instrument of always, the camera system, which is a fantastic machine, and which is under Italian leadership, and where we have the co-PI and at DLR, and there are other German contributions. And of course, it's a very international thing. It's a European mission with contributions also from Japan, from the Jet Propulsion Laboratory, from Brazilians, from all over the world, so to say, where scientists deal with the solar system. There's another mission coming soon, which complements nicely the JUICE mission, which is NASA's Europa Clipper, which will be launched next year, which will arrive earlier, and which is dedicated mainly or almost entirely to the exploration of Jupiter's moon Europa. I will not go into details with that missions, but it doesn't go into orbit around Europa. It will go in an orbit around Jupiter, but will have dozens of close flybys of Europa and observe this moon in much more detail than JUICE can do. JUICE will have 2 flybys at Europa 2, but will have much more flybys at Ganymede and at Callisto during its Jupiter orbit phase. And finally, and that's a first for JUICE. JUICE will be the first mission that will enter a moon's orbit at the end of the mission at 2034-35. And this has never done before, except of our own moon at the Earth. And so these 2 missions are really wonderful in complementing each other and getting good results on the science objectives and the questions we have. This is the JUICE science objectives, and of course it deals with the Galilean moons. We call them Galilean moons since Galileo Galilei discovered them in 1610. It will also observe a little bit some of the minor moons. You might know that Jupiter now has 95 moons, and 91 of those are really small ones and have extreme orbits and shapes and things like that. It will have the opportunity to observe a few of them. It will look into Jupiter's faint rings, which we have only done with Galileo and a bit with the Voyager missions. So there are a lot of hidden aspects we don't know about the rings. It will look into Jupiter's atmosphere, although there's the Juno missions, and I will show you some wonderful examples of Jupiter images from the Juno mission in a minute. It will measure Jupiter's magnetosphere, which is the strongest beside the sun's magnetosphere in the solar system. And we don't understand it fully, where it's created and how its shape is and how its dynamic is. And of course, Jupiter could be a role model for extrasolar planets. We already have discovered 6,000 of them. And at least, I don't know how many of these 6,000 have moons, but they certainly will have moons. We are not yet able technically to observe them, to discover them. But since this is here in the solar system, a solar system of its own, this might be the case also in extrasolar worlds. And this is also an aspect of the science objectives. When I prepared the talk yesterday, I thought that we are still able to see Jupiter, but this is not the case. It's only Venus, very bright at the moment. And we have a big Venus conference in Berlin the next 4 days. Venus is the next hot thing in the solar system and will be the target of 3 missions of ESA and NASA at the end of this decade and the early next decade. And Jupiter is now visible before dawn, so that's a bit of a problem for me because it's very, very early. This is a very famous sketch from Galileo Galilei, 1610, when he received these lenses from this Dutch lens maker, in 1609, then he built his first telescope. You know these stories probably. And he looked to Venus, he looked to the moon, and he looked to Jupiter. And all three of these observations made clear to him that what Nicolaus Copernicus published about 60 years ago was right. The Earth is not in the center of the solar system, it's the sun. And this all fits very nice. And I don't have to explain the sketch. You realize there's a big circle, that's Jupiter, and there are these 4 stars with changing positions. So it was clear that Jupiter has satellites of its own, like the Earth with the moon. And so these 4 big satellites are named in honor to Galileo Galilei. So far, we have visited Jupiter several times with flybys of the Pioneer missions, which have not so much a scientific impact because they were primarily thought to prove whether spacecraft can pass the asteroid belt without damage, and that worked well. But the following 2 missions are legendary. These are the 2 Voyager missions, which passed Jupiter in 1979, and they passed Saturn, and Voyager 2 passed Uranus and Neptune, and both are now, I think, both are now beyond 20 billion kilometers from the sun. One was very close to it recently. I don't know whether it crossed now the 20 billion kilometers line, and they are basically outside the solar system, at least outside the magnetosphere of the solar system. And they made wonderful pictures, as you could see, which caused appetite for a new mission, and that was the Galileo mission, which operated in the Jupiter system from 1995 to 2003. What you see here at the parachute is not the Galileo probe, of course. It's a probe that dived into the atmosphere of Jupiter and transmitted data for about, I think it's almost 2 hours until it got squeezed from the pressure. And the Galileo probe orbited Jupiter and the moons for 8 more years, almost 8 more years. Then there was a flyby by the Cassini mission, which also yielded nice photographs from the flyby and the acceleration to the Saturn system. And finally, the New Horizons flyby in 2007 on the way to Pluto. And then there was the Juno mission, which was inserted into orbit in 2016. It's also 7 years now, and makes wonderful pictures I show you now. These images are so incredible, beautiful, and it's a legendary mission already. It wasn't thought to last that long, and now they're yielding really wonderful pictures. And what is worth mentioning is that this person here, Kevin M. Gill, he's kind of a citizen science project to work with the scientific image data to make visible effects that are both artists' work and scientifically worth of being examined on the dynamics of the Jovian atmosphere. And they are unbelievable beautiful. And Sabine will be inspired by these pictures probably to paint immediately images from gas giant planets like Jupiter with its high pressure and low pressure systems. And I think the weather there is not really nice. And this, of course, is the famous red spot, great red spot of Jupiter, which some say Galileo Galilei discovered it, but that's probably not true. It's not the case. It's confirmed only since the mid of the 19th century, but probably was discovered in the 18th century already. And it's getting smaller these decades, you must say. It originally had a diameter of 2 Earths, and it's now significantly smaller. And who knows whether it will disappear sometime and some other spot will appear on some other place. Here, another picture, which looks really like artwork. And this is a photo that shows the shadow of Ganymede to the left. And this leads me to get a few informations about Jupiter. Of course, it's the biggest planet in the solar systems. We all know this. It's when I have school kids, it's really easy to tell them 10 times the diameter of the Earth. It's 1 time the diameter of Jupiter. And 10 times the diameter of Jupiter, that's 1 time the diameter of the Sun, and 1.4 million kilometers. And even though this picture already is really spectacular and shows the insignificance of the terrestrial planets, Mercury, Venus, Earth, and Mars, the next one is even more impressive, and you have difficulties with weak eyes to see the terrestrial planets, and that shows you, of course, that what kind of exception it is that we have this presentation tonight. So meaning that life exists on this very little cent grain, or however you want to name it. Yes. 99% of the mass of the solar system are in the Sun, and the rest is in these 8 planets and the asteroids and the comets. And from this 1%, again, more than 2/3 are in Jupiter. So it's a nice coincidence, I think, that Earth exists and we have oceans and we have life and we are sitting together and talking about this. This leads me to the big questions we have since thousands of years of astronomy and 400 years of the telescope and not even 100 years of spacecraft. So we are now able to find out how unique our solar system really is. We are part of the Milky Way, this galaxy with 200 or 300 billion stars orbited by a couple of hundreds of million or even billions of planets. So do we have something that's really similar to the solar system, comparable, about the same, with a star like our Sun, with a planet like Earth in the right distance, orbiting, circling around its axis and developing life? Yeah. How unique is this? This will be one of the big astronomical questions of this century and the future centuries probably too. Are there other places for life? So let's look first in our solar system. Then we can have a look onto planets and distant stars with maybe improving technologies. I'm not optimistic that spacecraft will ever be traveling to distant stars and distant planets. But that's another question. I mean, that's reaching too far for tonight. And how could we find out? Of course, if we take the tools we have, the spacecraft, the instruments we build in our universities and laboratories, and send them on spacecraft, on space probes, on orbiters to these places of interest in the solar system. And we find out maybe, I don't know how fast, we will see. So the JUICE mission is a very fundamental part of this, answering these questions. And before that, we had the Galileo mission, of course, which raised the appetite for the JUICE mission. Initially, Galileo had a big problem because of the Challenger accident. It was stored 2 more years until launch. And this launch led to a problem with the main antenna that couldn't unfold after this storage anymore, because the ribs of the antenna did not work anymore properly. So they only could send data back to Earth with a small with a small antenna. But at the end, the mission was extended several times. So we got beautiful images from all the 4 Galilean satellites, Ganymede, Callisto, Io, and Europa. Let's compare them a bit with other satellites, other moons of planets, and with Mercury, the smallest planet in the solar system. So you get an idea. Ganymede is the biggest, Titan of Saturn, the 2nd biggest, and Callisto, the 3rd biggest. Then there comes Io, the moon, Europa. Triton is of Neptune. Pluto is no longer a planet, unfortunately, and Titania. So let's have a look on these target planets of JUICE. Io is not so much a target of the mission because it's so close to Jupiter and the radiation environment there's really heavy. So the electronics of spacecraft and the experiments would have needed much more shielding that it already was provided to the experiments. So this would have meant that the payload would have become even more mass, and mass is always money, because you need stronger carriers and more fuel. And so they said, IO, we do not observe from close up, but from far away. It's the most active body in the solar system regarding geology, because it's always creating magmas in its interior, and has several active volcanoes all the time, and they are big volcanoes with eruptions reaching 200-300 kilometers high. It's a silica volcanism, and it's very mafic, so very low in silica and rich in iron and magnesium. And as I said, it experiences, the body experiences extreme tidal forces. So that's also the reason why Io is not an icy moon of Jupiter, because all its volatile elements, the light elements, have been blown away or lost to space, so to say. And so Io has only its rocky remnants, and it's a big moon, of course, and it's very nice. It looks like a pizza when you look at it, and these activities are wonderful. When we had the Galileo mission, we saw changes on its surface of really big volcanic eruptions, like here between April and September 97. An area about half the size of Germany was changed in its surface with dark sulfur-rich lavas, and they oxidized later and got this red and yellow tone. So it's changing permanently its surface, and has really hot volcanic spots with eruption as hot as 1,400, 1,500 degrees centigrade. Here, a caldera of a big volcano, about the size of, it's much bigger than the Hawaiian volcanoes. It's really a diameter of more than 100 kilometers, and with molten magma. And also New Horizons observed eruptions against the horizon, as you can see in this right of the two images, where the balance of the camera was programmed to film one of these umbrella-like eruptions. And on the right, you see the distance geometry of New Horizons on its way to Pluto. So the distance to Jupiter was 0.02 astronomical units, so that's about 1.5 million kilometers, 3 million kilometers, and that also demonstrates how powerful this camera on board of New Horizons is. And beyond Io are these three big icy satellites. Next comes Europa, then comes Ganymede, and the outermost is Callisto. And they all have icy surfaces, because so far away from the sun, the temperatures are extremely low, minus 150 degrees in average on the surface of these moons. In their interiors, which we will talk about in a minute, it's completely different, but the surface is icy. Of course, you think, when you think about ice is bright white or transparent evenly. You see this is a bit different. This is also because there are other materials on the surface. What you see as brown spot on this color enhanced image of Europa, these are minerals that come either from the outside, from impacts on the surface of Mars, or from the inside. We will talk about this. And Ganymede looks completely different, and you see, or you get an idea already that there was a lot of dynamics when the surface was created. And Callisto looks a bit dull, like a evenly distributed surface, a uniform surface with a lot of impact craters in the ice, but also with colors, so to say, that show that other materials came on top of the pure water ice on the surface. But that's the interesting thing when we look inside these planets, which we of course cannot do with cameras or with drilling or whatever. But with modeling from the geophysicists, we see a lot of interesting things. And of course, it's the water that's inside of these moons. Europa almost certainly has almost directly under the surface a big ocean. It's very likely that this is the case. And this should also be the case for Ganymede, but it's deeper then. And JUICE should find out from in its orbital phase around Ganymede whether this ocean exists indeed. And this is a bit an older display of Callisto. Callisto now is also thought to have an ocean inside. We will see this in a moment. So how is it possible when it's so cold in the outer solar system that there is water which needs energy to not freezing? And of course, this has to do with Jupiter and its gigantic mass, which attracts these moons. And from the elliptical orbits around Jupiter, there are tidal forces. So there's tidal freezing and a tidal squeezing on the innermost planets. I always call them planets. They are moons, of course, of Io, which creates the magmas, which affects Europa, where we have the water ocean, the liquid water ocean, and some, you see this from the red tones and the rocky mantle of Europa, also probably some melting of rocks inside the rocky mantle. And this is also very important, which we will see in a minute. And another effect, which is named resonances. The three innermost moons are orbiting Jupiter in a resonance. So when Ganymede is orbiting Jupiter once, then Europa is doing that twice, and Io is doing it 4 times. So, and then you have several constellations when they're in one line, and then you have resonance effects which add to the tidal forces of Jupiter. And of course, this adds another amount of energy to the interior of these bodies and creates heat that keeps the water molten inside of these moons. Let's have a look on all of these 3 moons. First, from the outside to the inside, Callisto is quite a bit bigger than our moon, with 4,820 kilometers diameter. And it is comparable to Ganymede, but it is probably only almost not differentiated. With the differentiation, we mean the separation of the heaviest materials to form a core, usually iron or metal-rich ingredients, surrounded by a mantle of rocks and covered by a crust of lighter elements, in that case, frozen water, ice. Callisto has no signs of current geological activity. It is probably one of the oldest surfaces in the solar system. Almost all areas are thought to be older than 4 billion years because we have so many craters on the surface. So a very interesting target. And in the interior, probably an ocean. It's not entirely proven, and we will hopefully find out with the JUICE mission. On Callisto, you find one of the biggest, or maybe even the biggest impact basin in the solar system. It's called Valhalla. It has this multi-ring circular structure we have here on the image. We have some scarps that show that there was some tectonic activity. You know, it's a close-up that shows a several 100-meter high ridge where we have a long shadow. So there was some tectonic activity. And when we look more into detail into Valhalla, we see that we call these palimpsests from the papers they had in the antique times to write on, and which you could erase what you have written on it, but the old thing still is visible on the surface, what you have written. And at the end, we found out that this impact basin is 3,000 kilometers in diameter. So that's quite a big thing. It's even bigger than the South Pole Aitken Basin on the Moon or the Hellas Impact Basin on Mars. Let's have a look at Ganymede, the biggest moon in the solar system with more than 5,000 kilometers diameter. Ganymede certainly is differentiated into a core, a mantle, and a crust. And between the crust and the mantle, there is probably a big layer of an ocean, or ocean and ice, or one of the two, or both of the two. Ganymede has its own magnetic dipole field, which is the only one of only significant one of a moon in the solar system. And when you look at the image, it's obvious that you have a quite intensive geological past, and you have tectonic structures. You have, if the ocean exists, then it must be really big and has more water than all the oceans on the Earth combined. Let's have a look at a couple of these structures. I remember well when in 1907 and July, we had the first images like these, and to the late Gerhard Neukum, I told, this looks like a close-up from the elephant in the zoo. And he said, no, this is Ganymede. Bernard will remember how Gerhard was very impulsive. And it showed us two things. The first thing is the camera worked perfectly. It's a wonderful instrument, and it's a pity that the main antenna did not work better than due to this not accident, this technical problem. And what you see here is quite easy stratigraphic situation. You have the old terrain surrounding two tectonically stretched areas which are cut. So you have 1, 2, 3, easy to find out what is older, what is younger. And we have several of these areas, and we could even make 3D animations where we had stereo coverage, and our Bernd Giese made these images, and that showed how these multi-rich areas have been stretched by tectonic forces in a time about 3.5 to 4 billion years ago. Ganymede today is geologically very likely inactive. We have not seen any sign of geologic activity, too many craters, too thick the crust, but nevertheless, we found wonderful, unusual landscapes in icy tectonics, cryovolcanism, which means that there must have been a time when water was pressed through the surface, froze out, and formed these landscapes. And then there came impacts, and from the impacts, we could determine the ages of these surfaces. Yeah, Jim Head, the geologist at Brown University, he discovered this area here, thought this might be an area where we have a rather young, or one of the latest areas where cryovolcanism occurred on Ganymede. And it looks like there was some slushy material, probably mixture of ice, rocks, or only ice, water ice, and that froze out. And so we can see today there are few less craters than on the surrounding. So this could be one of the real signs of cryovolcanism. Also this too, where we have this flat area at the center, or some other areas too. We have no global coverage of high-resolution images of Ganymede, and that's one of the reasons why we developed the JUICE mission with a camera system in a way so that Ganymede will be covered now globally to get a better image on this. There was a recent flyby of the Juno mission and showed also some nice areas which we have not seen before, like this fresh young impact that must have occurred, I don't know, 10,000, 100,000 million years ago. So Ganymede is a prime target of the JUICE mission. Finally, Europa. Europa is supposed to be the hottest candidate for searching for life in the outer solar system. On the left, you see a true color image, and when you enhance the contrast in the in the individual filters to create this color image, then you see even more details in landscape and get some idea of this world, where you see on the first side there are almost no impact craters. Yeah, there's this one bright spot on the right, lower right. There's another one on the left, which could also be a caldera. We are not sure about this. So it's a young surface. A young surface means there must be a process that resurfaces the surface. So because impacts are occurring since 4.5 billion years. And when there are only very few markings of these impacts on a surface, this means it must be a young surface that's resurfaced by any kind of a process. And this probably was water pressed out by these cracks that looks like the traces of a skater on the ice. And sometimes these cracks opened and pressed out the water that froze out, even better visible here. And you see curvatures of these cracks, which means that the ice might have been shifted on a more liquid medium, on a more on a slushy ice layer might be. We don't know this precise. I show you in the next image some really crazy things, what we have discovered with the Galileo mission on Europa, which of course is the perfect example of a planet that must have been active in recent times, because it looks also fresh and young. And these are a couple of surface features on Europa. I'll show it in more detail here, where you probably have ice rafts that broke apart by forces that from underneath that moved the surface. So it cracked up and was drifting like ice blocks, like icebergs in the Arctic or in the Antarctic. And you can reconstruct from the geometry of these icebergs how the plate looked like before it broke up. And all this must have been in geologically recent times, meaning only millions or tens of millions or even 100,000 of years ago. And so we think there's a layer of liquids underneath that drives these processes. Here's Connemara Chaos in detail. It's an area about the size of Berlin or London or Paris, 50 by 35 kilometers. And you see how it looks like. Very, very interesting. And when you go to the highest resolution images of Galileo, you see really tectonic features where a crack opened about the size of the Titanic. That was an idea of Jim Head 15 years ago or 20 years ago, and I found it very cool to compare it in size. The Titanic would have disappeared there, this crack maybe. Galileo had a camera with, I can't remember, 7 color filters. And when you combine these color filters, you also get an idea about the mineralogy of the surface. And we found out that, of course, there's water ice, but these colored stuffs are minerals. And we are very much convinced that these minerals have been coming from the ocean water underneath. So this ocean under the surface of Europa has salts, soluted in the water. And when the water was pressed on the surface, it froze out, and these salts are visible. There magnesium salts, calcium salts. There was also a spectrometer on board of Galileo, which has physically, this is not possible with the same resolution, but with a 10 times lower resolution, that gave also hints about the composition of these salts on the surface. So when you have salts, this also means that there's something going on in this layer under the surface of Europa. These are now recent images from the Juno mission. Again, here also close-up details. Again, completely weird landscapes. And there are things we don't have no idea what it is. Is this a cryovolcano with a caldera in its center, or what is it? At least it's something really fresh, because it's younger than all these tectonic structures surrounding it because it's cutting them off and resurfaces the ridges. So we are really wondering what's under the crust of Europa. So that's the big question. There are models, of course, that if you have this resurfacing, then the ocean could not be very deep under the surface, because otherwise the water would not reach the surface, even from the tidal deformation of the crust, when it breaks up these ridges. So there's the one model that says we have a big, deep ocean, about 3 kilometers, maybe in 10 kilometers depth, which is about 100 to 200 kilometers deep. Some say 120 kilometers is a good number. And this water of the water of this ocean is circulating in the rocky mantle underneath. And this rocky mantle is hot, is volcanically active, like the Earth ocean's floor also are active areas. And when you have hot water circulating into the rocky mantle, you solute out minerals from the rocks, and these minerals get into this ocean. So you have a salty soup, maybe comparable to the Earth's ocean. And we know from the Earth's ocean that life, very likely, or it's a good model, that life started in the oceans at these, what we call hot black smokers and white smokers, because you don't need sunlight for life to exist. And these black smokers in the terrestrial oceans are the best example for plenty of life forms existing there in depths where no sun ray is ever coming that deep. The right is a bit a different model with a thicker icy crust with some plumes rising in this icy crust. So it's slushy, it's not really very brittle. And you have a smaller ocean underneath, but also in contact with the rocky mantle of Europa. That is something we might find out with JUICE to some extent, but to a much bigger extent with the Europa Clipper of NASA. And that shows that these two missions are complementary. Here's a bit of an idea about what happens to these molecules that are in the ocean under the crust of Europa when they come to the surface, when they spoon out like geysers in Yellowstone or in Iceland, and they are then exposed to charged particles, radiation from space, and the molecules break down. And you might know these tow lines that are on the surface of Pluto or of Titan, and nitrogen molecules. So this is the chemical situation we have not yet really a good idea about at Europa, but the spectrometers and the two missions will find out then. So the artists that deal with this data we have from the science side, they make their pictures, and this is a very wonderful image. I think that's how it might look like on the surface of Europa, and directly under the crust might be these oceans 100 to 200 kilometers deep. And here again, an image of one of these models, how it can look if we would cut into the sphere of Europa. Again, here are some models compared all these three. Europa is the moon which is closest to Jupiter, so it receives most energy from this tidal deformation. And so this ocean is directly underneath the crust. It's different with Ganymede, where it's much deeper. So the preconditions for forming life there are different. Talk to the biologists why this is the case. It's higher pressure, of course, so it's might be not the first place to look for life. We cannot look at the moment, so JUICE will not find out whether there's life on these oceans. And so it's this ocean is between two ice layers. The lower layer, a high pressure form of ice, and then there are rocks in the core. And with Callisto, it's a bit different. Callisto probably does not have a core. It's a uniform mixture of ice and rocks in its interior, but maybe also with a 100-kilometer deep ocean under the icy crust. Yeah. We have this, here again the inner structure of all the 4 moons. This was done by ESA Io without any icy components because it's too close to Jupiter. Europa with a ocean directly under the surface, and then a rocky mantle where a lot of things occur because of a lot of heat. And then Ganymede with a deeper laying ocean, and also a rocky mantle and a big iron core, which is important for the creation of its magnetic field. And Callisto, which is a rather undifferentiated world, but also with the ocean under thick icy crust. Okay, so I'm not a geophysicist and I don't know very much about magnetic fields, but of course the magnetic fields of Jupiter and Ganymede are important. So I try to get my little knowledge about magnetic fields to you, and there have been measurements induced magnetic fields at Callisto and Europa, but the interesting thing is with Ganymede. Ganymede has also an induced magnetic field, but it has also an intrinsic magnetic field. So it creates its own magnetic field, and this interacts, of course, with a big magnetic field that's from Jupiter. So the magnetic fields of Callisto and Europa are coming from Jupiter's magnetic field. You see it here a little bit. No, this is not what I want to show. The next one is, so the blue stuff is Ganymede's magnetic field, and it when it's coming into, or when it's orbiting Jupiter, then it interacts with a dynamic magnetic field of Jupiter, which is the brown field line, which are the brown field lines. And these interaction you can measure in the direction and the strength of the field lines of both magnetic fields. And this led also to the observation of the ocean inside of Ganymede. It's shown here dynamically with also an ESA sketch movie very nicely. You see the polar lights at the poles of Jupiter. So this is the interaction with the intrinsic magnetic, with the induced magnetic field of Callisto. And then you see the same for Ganymede, where you have 2 magnetic fields, so the things are more complicated. So Ganymede will also have its polar lights from its intrinsic magnetic field. And with Europa, it's again different, which doesn't have an intrinsic magnetic field. So it's a bit wild, and I do not fully understand the movement. But of course, you see the dynamics and you see changes, and that's something you can measure. And everything you can measure leads to results, to scientific results finally. And this is the magnetic task of the JUICE mission, which of course has a big magnetic boom, which will measure the field strength of all these moons and in how they interact with Jupiter. I just want to mention that beside the icy moons of Jupiter, there are 3 places that are also of interest regarding the possibility of oceans under the surface in the outer solar system. That's Saturn's moon Titan, which has been observed intensively by the Cassini mission. Then Saturn's moon Enceladus, which was observed also by Cassini, a very small moon, only 500 kilometers diameter. And Neptune's moon Triton, which has been visited only once by the Voyager 2 mission in I think it was 86 or was it 88? I'm not sure anymore. And which should be the target of one of the future missions. Of course, it's really far out and it's not easy to reach, but Neptune shows signs of activity on its surface, which makes it very interesting. And there was a news yesterday, I think, that modelers also think that the satellites of Uranus could contain water oceans and the potential of life. So let's finally come to the mission Choose, which will be the last part of my talk. It's a big spacecraft, of course, with it's 6 tons of mass, and it has 11 experiments. I will show you all experiments, but not go into too much detail. You see big solar arrays, and I think I have it right here. Yes, I do. That shows how big these solar arrays are. They are almost 100 square meters in area, and this shows a test to unfold them at Airbus in, I don't know whether it's Friedrichshafen or it's in Toulouse. They showed it at the beginning. I did not pay attention. And of course, this demonstrates that it's a critical moment of the mission shortly after launch to unfold the solar arrays, these 85 square meters to produce power. But at least it's possible to create power in the distance of 5 astronomical units where Jupiter orbits the sun, and where you only have 1/25 of solar power than on Earth, because it's going down with a square of the distance. Yeah? And with Galileo, this was not possible. So Juno also not, but now it's the first time we can observe in 780 million kilometers distance a planet with solar power. I don't know. I don't go in all the details of the experiments, but of course, when you go to a target so far away, which you will do only once in 30 years as a space agency, you put everything you can do on such a mission. And it starts with a camera, the Janus camera, which is Italian design, and it's really a wonderful camera. They told me you can distinguish a tennis ball from a distance of 100 kilometers. Yeah, I can't remember. But you see, you have 7.5 meters of pixels at the best resolution, which is not the complete truth. There might be even a mission phase at the very end when you have 2.8 meters per pixel, if there's enough fuel left from when that Choose can go down from its last 500 kilometer orbit around Ganymede to a 200 kilometer orbit. And that would be, of course, sensational. Yeah? And we have 11 filters in this camera, so you can make multispectral imaging and getting also important information on the mineralogy on the surface of Ganymede, Callisto, and Europa. And of course, it's the instrument it's the eyes of the mission, and you can do all the geology with it. It will also look into the dynamics of the Jovian atmosphere. Yeah. Then you have various spectrometers, one for the visible until the near infrared to 5.7 micrometers, also with very good resolution for the Ganymede phase of the mission. And this will provide us the surface composition of these salts, or is this material from outside, from comets or asteroids. And you have a UV spectrometer, which is the other side of the visible spectrum. And this will deal more with the aurora and air glow of both Ganymede and Jupiter, the surface brightnesses, and other aspects of observation, astronomical observations. We have a sub-millimeter wave instrument, which works at wavelengths of 600 gigahertz, which looks more into the stratosphere, deep in the Jovian atmosphere, and will observe also the atmosphere of Ganymede, which has a tiny, tiny atmosphere, which we rather call exosphere. Then you have Gala. I will describe this in a minute because it's our instrument. You have an ice-penetrating radar, which will not go probably as deep as the ocean on Europa is, but you can read penetration up to 9 kilometers. And so that's a very, very interesting instrument. And then the second page of these instruments is you have a magnetometer, which is of course measuring all this magnetic field data I told about. You have a particle environment package, because there are a lot of tiny particles cruising around in the Jovian environment, and it measures the speed of these particles, how they are ionized, how strong, and so on. You have radio and plasma wave investigation, where you have a magnetic field. You have also plasma waves, and these are physical experiments. I cannot talk much about it because I'm a geologist. Then you have a very important instrument that deals with the gravity geophysics of the Galilean moons, which is important to get information on the interior layered structure of the 3 moons. And you have a planetary radio interferometer, Doppler experiment, so to say, that is very important also for the precision of other measurements, and which can very precisely determine the ephemerides, the position of the moons, and maybe we have to change some information there. And this is also very important. Okay, I show you pictures of the 2 instruments where we provided some hardware. Left is the Gala laser altimeter, where the optics and this came from a German industrial partner, and the most of the electronic parts came from DLR in Berlin. The principle is basically that you shoot lasers with this. I put my mouse here, I hope you see it, on this laser gun to the surface of the targets, Europa, Ganymede, and Callisto, and you wait for the laser pulse to be reflected in return, and you catch the return signal in the big telescope here. The thing is about microwave oven size upright, and the time the laser pulse is running to the surface and back is a measure for the distance. And when you know the position of the spacecraft precisely, you can determine whether you have a mountain there or whether you have a valley there. You shoot about 20 to 30 times per second, so you get really a dense coverage of the area under the spacecraft. And in the case of Ganymede, you get really a global coverage and of the topography of Ganymede and of the shape of Ganymede. And that's the cool thing of this experiment. They will be able to measure during the time of the orbital phase how Ganymede is deformed by the tidal forces of Jupiter and the resonance effects of the other moons. And with such a precision of less than a meter, in cases of only some tens of centimeters. And when they found out that Ganymede is deforming more than 6, 7, 8, 9, or 10 meters in shape, that's shaping the sphere of the body of Ganymede, then they are sure there is some really big liquid layer under the surface. If these measurements show it's a deformation of only 1 meter, then they know there's probably no ocean of liquid water under the surface. So that's one of the key instruments to find out whether Ganymede has an ocean under its surface. The camera I already described to you. Here's another image in the laboratory with Nicole Schmitz doing the last handwork on it before we delivered it. You see it here. That's so the optics was made in Italy, and the electronic boxes came from us, and we also worked on the sensor of it. And so these are 2 instruments from us, from DLR, or where we have been partner of it. Launch, I don't have to explain to you. It was an Ariane 5 routine launch, not going into Earth orbit to check out, but going directly on a on an orbit around the sun. That's why the launch has to be second with a precision of seconds. So you could not be shifting it minutes or even hours. So you have to be really precisely on seconds. And so that's why they stopped the first countdown on the first day and then repeated it almost in the same time for the next day. These are the usual acceleration steps in the inner solar systems with gravity assist maneuvers. So next year in August, we will have a lunar Earth flyby, which is also a first in space flight. So JUICE will come from behind the moon and use the moon as an accelerator, and then Earth 2, which we have not done, which nobody has done before. And we will have nice lunar observations with the instruments and with the camera in particular. And this will make me happy because at least this is done before I get retired in 7 years, because it will take 8 years to reach Jupiter in 2031. Then there is another Venus flyby, an Earth flyby, another Earth flyby, and then the arrival at Jupiter in 2031. And you see that the ellipse of the orbit around Sun will always increase higher and higher and higher until it will be able to reach Jupiter. And this is displayed here in another ESA video, which is really nice. And we have this Moon Earth flyby. I hope you can see that it's not so much interrupted. Another one with Sun, Venus gravity assist maneuver. Also with nice observations. Cloudy world. 2 more Earth flybys. You see Jupiter waiting there by the solar system. Final flyby at Earth. Falling in, and going to check it. And the arrival of Ganymede and Jupiter. First close flyby, 500 kilometers. Nothing. Will be a long ellipse, several million, I think 18 million kilometers out. When returning, slowly getting really captured by Jupiter. With only little fuel to be used, that's good, but of course you need some orbital trim maneuvers. From the 2 important Europa flybys. These are the closest of the entire mission. It's very important in 2032. And a lot of Callisto flybys, 21 in total. When they increase the inclination, so we can see other regions of Callisto, mainly, and Ganymede too. And finally, they get into Ganymede orbit. And then These orbits gets more and more circular. And if you're lucky, we have still some fuel left to go into a lower orbit, about 200 kilometers altitude, and getting the best images of Ganymede. Finally, it is said there was the impact on the icy crust of Ganymede, which is no problem with planetary protection regulations, because we assume that the ocean of Ganymede is so deep that there's no chance of contamination for the ocean of Ganymede. I show you at the very end, I show you a couple of funny things. Here you see what with the blue line, you see what we have seen in the video just now, the arrival at Jupiter and the very long ellipse that reaches out 18 million kilometers. Look at the bottom of this image, you see the distance between Earth and Moon and Mars, which is at closest at opposition about 60 million kilometers. So you get an idea that the radiuses of all these tiny satellites of Jupiter, they have radiuses of 30 million kilometers almost. And so we have a few opportunities to observe a couple of these irregular satellites that are orbiting. Orbiting is a good word for that, outside of Callisto's orbit. And also at the beginning, some of the smaller, but they are the biggest of the smallest satellites of Jupiter in the inside of Io's orbit. So this is Amalthea, Adrastea, Metis, and Thebe. And we will also have a look at the Gossamer rings of Jupiter. So this is an old image from the Galileo times. This will be very interesting too. And here you have a side view of all these orbits. And you see they have weird inclinations. So they're all captured asteroids probably, and not children of Jupiter itself, which is probably the case for the Galilean satellites, but not for those. And what you see is this red line in the center of the image. Is the radius to the left and to the right of Callisto. So the most distant of the innermost Galilean satellites. So what else do I have for you for the end? This is just an example to show you how we planned, or the teams planned already their close flybys and of all these, but during the orbital phase with blue flybys of Europa, yellow is Ganymede, and green is Callisto. So they're already on the second precisely planned for all these flybys, and this will last until November, end of 2034, with the last Ganymede flyby in the orbital plane of Jupiter, and then comes the close orbit at Ganymede. This gives you an idea about resolutions and distances of the flybys of Callisto, which are really good promising good image data. You see here the coverage we will reach for Callisto. It's a global map projection of Callisto. And you see we get about 10% with 200 meters per pixel. We get about 50% better than 1.52 kilometers per pixel. So really nice image data with which geologists can nicely work. Same is true for Europa, but of course not globally, which is not the task of the JUICE mission, but will be the task of the Europa Clipper mission that from NASA that will arrive then. And here you see the 3 orbits around Ganymede. And the GCO 500 is the most crucial orbit, which is a circular orbit in 500 kilometers altitude with good imaging conditions, so good phase angles with the sun. So we will get really global coverage. We get first the 5,000 kilometer orbit, but as I mentioned, at the end, 200 kilometers. So we get really global coverage, and I show you in a second how this works. This is this one. Oh, I gotta activate it. So that's the image planning already done for this orbital phase. You can imagine that planning of all these degrees of freedom you have, the movement of Ganymede around Jupiter, the occultations, the phase angle of the sun, and the rotation of the moon itself, and all this has to be calculated so you get the best results, a global map with uniform imaging conditions, lighting conditions, so you get 100% coverage at the end. And you see it's difficult to reach these 100%. We have the same problem with Mars Express and our stereo camera there. But they manage it. They say, except of the poles, which is due to the movement of the spacecraft, not possible. Almost complete coverage, 98%. That's the target. I will end with my favorite Galileo image of these days, of the Galileo mission time, which I really have framed at the wall, which I love because it has wonderful colors, and it's telling me histories about a wonderful time here at DLR when we had the Galileo mission. And here I stop in, well, plenty of time.
Yes, but I'm so fascinated. I love it when you talk. Really, your lectures are so precise, and you explain it. Even I'm not a scientist, but I understand it because you explain it in such a nice way. And
I made it only for you.
Oh, thank you. But really, I could listen to you hours. Yeah, you can give me private lectures if you want. I would listen to you. Yeah, but it's really, and also in the chat, I have comments that's from Paul Grefendorf. Wie immer souveräne, großartige Präsentation, Uli Köhler. Ich freue mich schon auf ein Wiedersehen Anfang Dezember in den Tagen der Raumfahrt. Freue ich mich auch. Sorry, this was the German, but all people right here. It was a really great lecture, and also the animation you have, and it makes it so understandable. You see, I'm really amazed. I will have you back here as a speaker. You have so many topics to talk about. So yeah. Also, we have people watching from Montreal, Canada, from Kuwait, from ExoTesla, and from Norway. Yeah, where Pierre is watching from, I don't know. We have from Dresden, Germany, and yeah, also really. And we have some questions also in the chat. Yeah, I really am amazed. I had also some questions. Pierre Rochus is asking, are you sure it is water? Couldn't it be another liquid type or?
It must be water because hydrogen is the most common, the most abundant element of all stars and the solar system. And Jupiter is also almost completely, or has the majority of its mass is from hydrogen. So when you have hydrogen and oxygen, which is also abundant in the outer solar system because it's a volatile element, then you have water. We don't know, of course, there's liquid methane, but you need a lot of carbon to make a methane ocean there, which is the case maybe at Titan, at Saturn to some extent, where you have methane lakes. That's true. But I'm not too much a geochemist to competently answer this question. Actually, I'm geologist and have to deal. It's an interesting question, and you found me a little bit confused about it. But I'm pretty sure that the answer is that you have too much. You have hydrogen in abundance, and you have oxygen in abundance, and it's the molecule that's easiest made in the outer solar system.
Okay. Great
But
presentation.
following that, maybe I could,
Yeah.
I mean, clearly we think it's mostly dominated by water, but there could be also some ingredients, some organics mixed, some from the contact with rocks and so on. And that's when it becomes interesting in terms of astrobiology, when you have not pure water, but dirty water.
Yeah, okay. It was clear that it's not clear water.
And that's why if we search for life, that's important to know if there is some communication between the surface that receives extraterrestrial organics, or also the subsurface where you can have also some element from rocks, and also you have a bit of a heating source.
Yeah. That's what we have at Enceladus in Saturn, where we have really the eruption layer of water contaminated, so to say, with organics.
Yeah.
And so this leads to the conclusion that they are perhaps good reservoirs for the origin of life.
And is it only salty water, or is there also sweet water? Because frozen water, it's normally...
It must be salty water, because the sweet water of Earth you only get when you have a water circulation where it drops out of clouds.
Okay. Then Pierre is also asking, what is the status of JUICE antenna? Is it deployed? Also, he means the RIME antenna.
As far as I heard, it's employed. Yes. There was a problem at the beginning, but I think they have solved it in the first week.
And moment. Also, Pierre is from Belgium. Hello. And
hello, Pierre. Bonjour.
Yeah. So, and knowing the highest level of radiation around Jupiter, how can we believe in life?
How can we believe what?
In life.
Because the radiation is not going that deep into the oceans.
Okay. And another question.
Belgium, by the way, was in Kourou for launch with his son. He's a space enthusiast.
Yeah.
Yeah. And
I was not.
And I have another question. This solar panel, how you can avoid that some impact from, when we go out of the Earth, we have all our satellites orbiting Earth, therefore we do it outside, but you have also other particles, asteroids, flying around, to say so. How can we avoid that it is destroying the surface of the solar panel?
You cannot avoid it, as you have seen at the James Webb Space Telescope. They had their first impact. This just happens, but statistically, you really got to have bad luck that a big impact would destroy a complete solar sail. So the experience from missions like Rosetta, which also had trajectory beyond Jupiter's orbit around the sun, I think there was no impact during 14 years of mission.
Okay.
So you have to rely on statistics. That you have to be lucky.
Have to have good luck, yeah. Wishful thinking. And another question, or what I found very interesting, is what you showed about the magnetic field, because with the poles, I know that Mars is like spinning around and has not the magnetic field like Earth has with the poles, and this was for me interesting to see in your lecture how you showed this that they were also rotating in all directions, also spinning around more or less. Yeah. Also it was very interesting. Bernard, so yeah, and the pictures I found, just a second, I wanted to mention they are really beautiful. And
it's really amazing that the magnetic field on the side outside, towards the outside of the solar system reaches almost as far as Saturn's orbit. So wow. It's an incredible structure. It's the biggest structure in the solar system.
Wow.
And of course, the circulation of the moons in this dynamic magnetic field, it's an extremely complex thing, but can tell us a lot about the inside of Ganymede and maybe Europa too.
Yeah. And the photos you showed, the artistic impression is really amazing, yeah. So Bernard has another question. Sorry.
but first, I mean, clearly, thanks so much, Uli, because not only you had a beautiful history of exploration, and then the narrative of the future, and understanding of what are the questions, and as well this great visual in terms of the best pictures of the Jupiter icy moons, but as well beautiful animations and very clear. So I think thanks for really this master effort to put all this together. It's a great show, and a great show for the eyes, for the mind as well. Also for the spirit, because of course you are asking some of the questions which are very important there about our origins, about search for life. Then you even shared some of the human adventure. I mean, this teamwork, we are all involved. So the engineers, the scientists, the managers, the industry.
Yes.
And so I have a question about that actually, because of course we have 31, and so how do we ensure that all the scientists, but also the engineers, the communicators, how do we ensure that we are continuing some activities to support how we will interpret the data, how we have shown beautiful planning of the mission. So everything is almost done. So what is left to do for the young generation? Also, what can we do in the laboratory or in theory to better prepare to what we are going to observe? And as well, how are we going to prepare to communicate it to the public? But at that time, we should communicate to billions of people when we arrive.
Yeah, it's a very important aspect what you mentioned, and I did not emphasize this enough. I think that it's really a giant mission for Europe, and we're doing really world-class science with that mission that will provide data that can be mined for decades. Definitely for decades, this will be data mining, and we have really a problem to find young engineers and young scientists. Of course, okay, the engineers, they have done their business; it's on the way. But of course, you need the engineers also during the mission time. As soon as something does not work so properly as you expected, you need the people that are not yet retired and know precisely how this thing works. And that's a big secret, for instance, for the HRSC camera on Mars Express, where the first are going close to retirement now. And we have really, it's not easy for us to replace them by young engineers and scientists, because that's a general problem in, I think, most of the European countries, that we have a lack of educated people to do this, because we are getting less just by numbers. I was last year at my school in South Germany, where we celebrated 40 years of Matura. And when we had Matura 40 years ago, we were 1,100 school kids there. Now it's only 500. So just by nature, it's getting less people. So it's really an issue. But the mission planning is, as you could see at the second precise flyby planning, it's already done. So of course they will use the camera and all the instruments to make flyby measurements and to calibrate the instruments again, so that when they arrive, they can be sure that the scientific data that's getting returned to Earth is so reliable that they can write their papers to publish scientific results that give us a new world, a new idea of the worlds of Jupiter, the icy worlds. So, but it's as you mentioned, and I think it's really important to use these 8 years until we arrive to enthusiast people, that they participate, that they share us to study physics, astronomy, chemistry, biology even, yeah, you know, and because astrobiology is a young discipline in astronomy, which is fantastic. It's really wonderful. I hope that I will still be alive when they find out whether there was life on Mars or there could be life on Europa.
Mm-hmm. Thank you. That's very inspiring.
Yes. Oh, and can't it be that is contaminated by us humans?
No.
No.
But in the case of the Jupiter worlds, because the Galileo mission was led into the atmosphere of Jupiter, there was nothing left. And when JUICE will crash on Ganymede, there will be at least tens of kilometers between the water ocean where we expect life to be and on the surface. It's different with other worlds like Europa. It would be not so nice. Planetary protection is a big issue in spaceflight since, I would say, 20 years or so. In the last century, they didn't really take care about that much. And we all remember that when the astronauts of Apollo 12 went to Surveyor 4 and broke off the parts and returned with them to Earth, they had bacteria from Earth there.
Yes, yes. Yeah, this is what I am thinking, and but also the instruments which are in space from us, because I saw the woman without mask working, and you showed the picture. So yeah, maybe there are some bacteria, or she even if she touched it with glass, but someone touched the glass with their hands or whatever, you know what I mean? And yeah, and for example, the space probe, Israeli space probe, how was the name of the space probe? Who crossed? Bereshit, yeah, genau, who crashed on the surface of the moon with tardigrades, thousands of tardigrades on board. So now the moon has life because the extremophiles, and I'm quite sure that they have survived.
It cannot be avoided because we are life. We humans, we are life.
Yeah, but
so we bring our life with us wherever we go, and therefore I think it's not.
But if there is a native life, we have to respect it. So we have first to figure out if there is life there, and then we have to decide how to protect some regions, not to destroy it.
Of course.
Yes.
Yeah.
Adriana, do you have some questions?
Let me add. Sorry, no. Well, let me thank you very much, Ulrich, for your beautiful lecture. I was fascinated from the first slide to the last one, and of course, all the animation were so okay. I wouldn't want to repeat what already Bernard and Sabine said, but it was really very, very useful and well explained, even for ignorant people about astronomy.
Non-scientists, you can say non-scientists.
Our ignorance is, but as Socrates used to say, we know that we don't know. Therefore,
yeah, I mean, I am the most ignorant as well, and I learned a lot.
Yeah. So, okay, I want to thank you very much, and I hope we can maybe have other conversation of this kind and to see some other things, because it's really, how can I say, a world that is opening to our eyes and perception, and and yes, too many questions arise about the possible life, and how it can work. And yeah, I also had a question in my mind, because you mentioned the organisms that live in the water, in the deep waters on Earth, where the sun never reach this deepness. So I was thinking, where do these organisms take the energy? Because
Sulfur.
Sorry,
Maybe from sulfur.
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 Yeah.
Mhm.
So
There's plenty of sulfur in the exhausts of volcanic gases and
yeah.
eruptions.
Okay.
I have another question. You said that could be a volcanic activity, but couldn't it be an impact? Because it looked for me, it looked like when I drop water into a surface and it sprinkles a little bit. You know what I mean?
Yeah, you have, of course, impact is also a form of transfer of energy from the outside to a system, and there are, of course, considerations that when you have impacts into water, ice, and things, that this gets so much energy into the system that you have the warmth and the energy to make molecule transitions and all these things, chemical reactions and all that this is possible. I mean, this is also one of the ideas how life came to Earth, that you have comets with hydrocarbon composition molecules, and when they impacted on Earth, that they get transferred to something else, and this might have been the precursors of life on Earth, and then evolution came and it changed. I do not know all about this, but of course, impact is an important energy source because it's really heavy energy, and of course, this can change things.
And if I can, sorry, you also spoke about radiations. And about someone asked how we could think about life with such a high level of radiation. I think that maybe there can exist also forms of life that were adapted to high levels of radiation, because even we on Earth, we tolerate a certain amount of radiation that reaches us through the atmosphere. It's very, very lower than what we get in space, but however, we are adapted to that. So why not forms of life that were born in that environment? Maybe they are adapted to higher levels of radiation. But my question is, maybe you said it, but could be that I missed something. What is the reason for such a high level of radiation around Jupiter? Is that has that something to do with the magnetic field, or yeah, is it
Yes.
so?
There's a zone inside Jupiter, several thousand kilometers deep, where hydrogen is so much under pressure that it loses its electron and it's get ionized.
I see.
So it gets metallic properties there, and this is in movement, and where you have then you have currents, and you have this strong magnetic field, and along this magnetic field, particles and ions get accelerated to a degree much stronger than in the Earth's magnetic field. These particles can be from the volcanic exhausts of Io, for example, could also be from the rings or from asteroids or small moons that are broken off and got to dust. And when they are accelerated, they are physical parts, and the radiation itself is so strong. I think it's 100 times stronger magnetic field than the Earth has, but I'm not sure about it.
I see. Okay.
Here's another question. Planetary protection is very important for ESA, even for missions like Solar Orbiter going in the opposite direction to the Sun. How can we accept the crash JUICE on Ganymede?
As I said before, that they are sure that even if there were microbes from Earth on the probe, and when they crash on the minus 150 degrees cold surface of Ganymede, there will be no contamination that reaches the ocean that is several tens of kilometers below the surface. It will never get through because there are no organisms that can survive this environment for longer than a couple of, I don't know, I'm not a biologist.
To the topic before.
Imagine yourself at minus 150 degrees. Won't
Yeah.
long.
From Innerleiten is the question, at what level are we in the development of radiation protection for manned missions to Jupiter?
I cannot answer this because I'm not from this field, but I think we are at the very beginning because there are no activities to travel with mankind to environments like Jupiter. It's hard enough to implement the results from the various Mars missions. There was, I think, with Curiosity, there was a dosimeter that measured the radiation levels in the crater where the Curiosity rover is since 10 years, and the result is rather depressive because it means that we need really strong protections even on a Martian environment, which also has no shielding magnetic field or Van Allen belt. So if you would travel with people to Mars, with the mission scenarios we have today, you have to stay there for a year up there. And what should you do in 1 year? You cannot wait inside one of these Coca-Cola.
Mars caves.
Yeah. I mean, you have to do something outside, some field work. And to do this field work without damaging your DNA and all these things, you have to be good protected. So
yeah, that's a big problem, I guess.
I think the moons of Jupiter are not really a target for the next couple of 100 years.
I guess so.
Actually, we made a study called Planetary Exploration 2061. And I mean, you know, the travel is a long travel. Okay, so you need protection during this travel. But if we have solved the problem for humans to Mars, and if we have a big ships, a big rocket like the SpaceX rocket, you could have a lot of protection. And then, of course, if you arrive at, for instance, Ganymede, then you would need to go to an ice cave.
Ice cave.
Because in the ice, you are protected from radiation. But it's true that with such a high radiation, in 1 week, you have as much radiation than, for instance, on the moon. And so you need to have a very good system. And for instance, these solar panels that we have on the JUICE, and also they are built by a company that is based in the Netherlands, actually. That's the same company that built the solar panel for Smart One, where we had the dose of 50 kilorad, as we say in our jargon. And they are so good that we will also use this same company to build the solar panel for Europa Clipper. So good European product. But that's true that you need a lot of development for protecting humans.
First of all, you need rocket scientists that make faster rockets.
Yes.
Propulsion.
You know, Uli, I really thank you so much for being with us for this really amazing lecture, for answering all these questions. And I hope I can convince you to come back. And yeah,
let's meet in Berlin.
Yes. Yeah, but yeah, we can meet in Berlin. We live not so far from each other. But would you come back for a lecture to us next year?
Yeah.
How could I say no?
Okay.
Thank you so much.
We are planning. We are planning for.
We are planning this, yeah, for next year. I call you. I thank you to the audience, and I would like to remind you that we are a non-profit organization. We are all working as volunteers here. So if you will become member of our association, we would be grateful to if you want to support us with your work or with becoming member, or if you want to donate something to us to make all this possible. And thank you again, Uli, for this amazing lecture, and Bernard and Adriano for joining us, for helping me as moderators. And yeah, I wish you all a nice evening. And I would like to remind you that the next webinar will be in 2 weeks, and we will have Tom Matula on the 22nd of May talking about an economic-based strategy for human expansion beyond Earth's boundaries.
Oh.
Yeah,
Thanks
so you are invited to join us too. You can always listen this and ask your questions. Yeah, we are always invited.
Thanks so much for flying
much.
us to the moons.
Yeah, for flying us to the moons and with Jewish. Okay, I wish you all a nice evening, and thank you so much.
Thank you.